All right, folks, we're going to get started. How's everybody doing today?
Good. How are you?
I'm doing well. Midterms, anyone? Anybody like had a lot of midterms this week? Oh yeah. All right, so we're going to be going more into the Ethereum protocol. So we're going to be covering a lot of stuff that we didn't cover after lecture 2. So that includes block structure, Merkle-Patricia tries. Basically, we're just going to keep going down the stack. So I'm going to recap a lot of stuff that we covered in lecture 2. We talked about Ethereum and how it's a platform to run smart contracts. It's essentially a distributed server, and it's not UTXO based. And transactions in Ethereum are essentially the manipulators in this whole state system. And we also talked about how you basically can model this whole thing as some kind of state machine. This state machine is shared and it's open to everyone. And there's this one single global truth that everybody focuses on. And it's cryptographically secure. We talked about how UTXOs are different than accounts, where UTXOs are essentially different components that compose someone's balance, whereas Ethereum has simply a balance that states someone's amount of ETH. We also talked about how accounts are responsible for the global shared state of Ethereum, where everybody, including contracts and owners, have accounts. And an account is represented by this 20-byte identifier. And we also talked about what kind of things are stored in the state. So we talked about how each account has a nonce, which is the number of transactions sent from that account, or it's the number of contracts that you've created if it's a contract account. And a fun fact is that basically each account and each transaction essentially has like a nonce linked to it. And every time you send a transaction from that account, you increment it. And every time you send like a specific transaction, it has a different nonce. And that's used to prevent any kind of replay attacks in the network. We also talked about how they have balances. We talked about how they have a storage root that's basically used to encode the hash of the storage contents of this account, because storage is kind of complex when it comes to Ethereum, and we're going to cover more of that. And we talked about how if you have code, it gets stored in code hash under the account, and this is like an optional field. We also talked about how this whole set of accounts composes the global state, and this is essentially what the blockchain is. And we talked about why accounts are possibly better than UTXOs. That includes space savings, that includes the intuition when programming in the protocol. There's also a lot of efficiency, comparable efficiency to using UTXOs, because you can still do SPV, as in you can still run light clients. We also talked about how externally owned accounts and contract accounts have different types of transactions they can work with. For example, an internal transaction is between two contract accounts, but a transaction is simply set in motion by some externally owned account. And a transaction can actually set off some kind of contract that makes another call to another contract, such that it generates an internal transaction. So we've seen this before. We also talked about gas, which was the payment method to use to pay for things like computation and storage on Ethereum. We talked about how in every transaction there's a gas limit and a gas price, and if you multiply these two, this is the max amount of Wei that someone is willing to pay for a transaction. And remember, just Wei is basically 1 to the 1e18. 1e18 Wei is 1 ETH. So if you look at 1e negative 18 ETH, it's basically 1 Wei. So it's a very, very small denomination of ETH. We talked about some examples of like when somebody executes a transaction. Basically, any unused gas gets sent back to the person, the initial sender. whenever we try to run things on this network. And if there's not enough gas, well, what ends up happening is it goes to the miners that ended up putting in the computation. And the state changes are reversed because the desired state that was meant to be changed wasn't able to complete because the execution was not able to complete due to the lack of gas. But because miners put in work, they get paid out. Fees end up going to the miner's address, and basically the higher gas price a sender is willing to pay, the more incentive the miner has to put your transaction in a block. And gas is also used to pay for storage. One interesting part of this is that storage is kind of expensive on Ethereum. It's kind of scarce. So any kind of transaction that like steps in and then clears an entry in storage, that fee ends up getting waived in a sense. Not completely, but there is a gas refund whenever you like free, right? So why do we need fees? We talked about this, and I think the main reason was because the halting problem. And that's because you can't tell when a program is going to stop running. And somebody can clearly DDoS the network if you don't have some kind of payment that's required in order to like run things on this whole computational system. So that's the biggest reason as to why there's gas. But also people need to be incentivized to like run things in the network in general. So there needs to be fees for storage. There needs to be fees for computation. We also talked about transactions, and essentially they are just the movers of state for an account. And we also talked about more formally how it's a cryptographically signed piece that's generated by some externally owned account, and then it's submitted to the blockchain. So if I'm running MetaMask, what that's doing is that is a light client that basically is sending a transaction to some kind of full node, and that full node will then broadcast it to the network and say, hey, this person is trying to make this transaction. It's cryptographically signed, so it can't be tampered with, and it includes a gas fee if it's completed honestly. And we also mentioned some of the components that come with gas. So there's a nonce that states the number of transactions sent by the address of the transaction sender. So remember that this is essentially it is unique to that like sender in the sense that every transaction sent by a certain person should have a different nonce. Otherwise, it's a quick invalidity test done by miners when they're looking at the transactions that are sent by your address. So a transaction also has gas price, gas limit. It has two. It has the amount of value. It also has the signature. It has VRS, which is used to generate the signature for the sender of the transaction. It also has an init parameter field in case you want to do a contract creating transaction. And it also has a data field, which only exists for message calls. Yeah?
What did the VDAR and the S mean?
Good question. Come to me afterwards. I'll have to like look it up again. So message calls and contract creating transactions are always initialized by these externally owned accounts, and you have to understand that transactions essentially bridge this whole external world to the internal state of Ethereum, and Ethereum just has these internal transactions that go on within the client level. So if you want to communicate between different contracts, you need to use messages. We also have the idea of nested message calls. I think this is pretty clear. All it's doing is you can have a transaction that sets off another internal transaction because it made a function call to some contract, and then from there that internal transaction makes another call to another contract, and you set off a whole chain. And essentially, the key thing about this is that the gas that the initial transaction had, i.e. the person that sent that transaction, is the gas that's there for all these next internal transactions that happen. So you can't really like change the gas like through this internal transaction afterwards. all the gas that you're going to use for execution needs to be specified in this very, very first transaction that sets off this chain of transactions. Yeah?
Where it says internal transaction, does that mean that they're calling a function marked internal?
Yeah, internal transaction is a message, and that's just like some function call like between a contract.
But like, you know how you can mark a function public or external or internal?
Yeah.
Like, is the internal that is written up there the same internal that's written next to the function?
Good question. Yeah, good question. So if it's internal, you're restricted within, I believe, the inherited contracts.
Yeah.
Yeah. So it's not the same because you can have public like contracts that send internal transactions that are technically like still internal because they're just interacting internally on the EVM, and that's what we mean by internal.
Oh, I see.
Yeah.
Okay.
So with that review in mind, I think it's time to move into more details about clients and consensus. So in the blockchain, there's this idea of global truth, and everybody accepts this in order to make some kind of progress in the system. And the truth is agreed upon via mining and peer validation, right? We saw this mining puzzle where it basically takes the hash of a block header. So that includes transaction data, that includes like the hash of the previous block, and then you concatenate that with the nonce, which is some number that you decide to change to make different hashes very easily. And then you need to have a hash that is less than or equal to the target difficulty, and that's just a way of saying my hash just needs to have a certain number of leading zeros. So let's suppose I have a hash that is generated from the block header I like proposed and the nonce I chose, and it looks like this. And there's 5 leading zeros in this, and in the target there's 4 leading zeros, and because there are more leading zeros in my hash than there are in my target, it's basically less than the target, and this is actually pretty rare to get through a SHA-256 hash. So then it's going to return true, and I have a valid block. And this is what miners will do to like find a block. They'll try to like brute force through combinations until they find this partial collision. And what people will do to validate is they will take the nonce and they will take the block header and they will simply hash it, and we'll just check if it's less than this the target. So once a miner comes up with this block, they'll basically kind of put it together into one piece. Like they'll put the nonce inside of it that they chose. They'll put the ordering of the transactions that they chose as well, because the ordering that which you hash the set of transactions like makes a difference, right? So like this block header, when you take the hash of it, it has something called the Merkle root. And when you generate a Merkle tree, it's very much dependent on the set of transactions you have, and ordering matters. So you can generate a lot of different combinations of hashes to come up with a valid block. So a bunch of people are probably generating different blocks in order to solve like this mining puzzle, not just because of the nonce, but also because of how transactions come in and how they're broadcasted and how everybody maintains a set of their own transactions. So once somebody comes up with a block, they take this block, they broadcast it to the whole network, and full nodes will essentially start to do the validation process. So we talked about this previously, but essentially this is the state transition code. Bitcoin is essentially client software that agrees on all these state transitions, and the state is, in this case, the ownership of everybody's Bitcoins, like who owns what UTXOs. And the state transition function is simply going to take the state, and it's going to take the set of transactions, and it's going to output some kind of new result. So I won't go through the function code too in depth, but essentially I kind of explained to you how Bitcoin already worked in that respect. But let's look at Ethereum, because we haven't seen this before quite yet. So Ethereum basically it's going to take a state, it's going to take a transaction, and it's going to basically apply this transaction to the current state and see what state comes out of it. So the first line, we check if the transaction is valid. We check if it's well formed. We check if the formatting is good. We check if all the parameters are filled in. And if that's the case, we move on. Otherwise, if it's not the case, if it's malformed, we return some kind of error. We need to also check if there's a valid signature based on like the sender that we had for that transaction as well. And we also need to check if the sender nonce equals the transaction nonce. And if it doesn't, we need to return an error. These should match clearly because the account, so the nonce for a person's account is essentially the number of transactions they've sent, and that should be linked to whatever transactions originate from that account. So if they don't match, it's very, very obvious like they've been trying to do like some kind of replay attack, or it's very, very obvious that they've at least like sent their transactions more times than they should have. So we should just clearly not like accept this transaction. And it's a very quick way for clients to say, no, don't use this transaction, instead of like having to traverse through more data structures. After we check those things, we calculate a fee based on the gas and the gas price that was specified in the transaction. We decrement that from the sender's balance. Then we increment the nonce from the transaction sender, and then we basically take our total gas and we subtract the gas per byte. We calculate a total number, so we have the total number of bytes from this transaction, and then we multiply it by the rate at which gas costs per byte, and then we subtract that from the total gas we have, and we run this function called transfer, and all it does is it'll basically, if there's no receiver, we create that receiver. We create that receiver address. And if the receiver is some kind of contract, we'll run the code to completion until the gas is out. And if it failed because there's not enough money or it ran out of gas, we revert all the state except fees, and we add the fees to the miner account. And if it's successful, we refund any kind of fees, any kind of remaining gas essentially that the sender like put into the transaction, and we then send the fees paid to the miner. Yeah.
So this, if you go back to the previous slide,
yeah.
The gas per byte is different for every miner?
Yeah, good question. It is.
So that means that if my gas per byte is pretty high,
yeah.
I may basically reject this transaction, but somebody who is ready to even process my request and his gas per byte is lower, then there is a higher chance he will accept that.
Yes, correct. He will probably end up running this, and he'll run it successfully, and he'll submit a block such that this ends up working out.
So here the gas equal to transaction dot gas minus this one. If this is minus, this miner is not going to keep all the gas, right? He will just refund everything. So
it might take up all the gas. It could, but in most cases you'll refund something.
Very pricey miner, right? Because his gas price per byte is pretty high. So that means that if my gas price per byte is pretty high, so whatever the transaction is coming to me, there is a higher chance that I may keeping all the money, right? Gas.
I don't quite follow.
So what I'm saying that this line, if it fails,
yeah,
you're gonna keep all the gas or you're gonna return it?
Yeah, so it actually now depends, but in this case, they will. So if the transaction fails, right? If they run out of gas, all the gas is kept, right? But if the transaction succeeds, then the gas is sent back. Any excess is sent back, and if it exceeds, it fails automatically. The transfer function would not go through. Yeah. Okay, and this is block validation for Ethereum. Block validation is very important because it ensures finality in our network, and that basically means like, how do we finalize any kind of block that gets submitted to the network, right? You need to have a miner generate that block, and then you need to propagate it to the network, and then you need people to, with running full nodes, you need them to validate that block, right? That you need them to say, okay, this is like a valid solution for the set of transactions that we have on this network. So the way it's done is we check if the previous block that it's pointing to is valid for the block that's been provided, and then we assert that the block timestamp that was given is greater than the previous block timestamp, but we also make sure that it's less than 15 minutes into the future. And then we check that there's a valid block number, there's a valid block difficulty, valid transaction route, valid uncle route, and we'll all like kind of cover these like smaller components that go into a block later. But we check if these block is essentially like is valid when it comes to these lower level parameters. And then we check if this is a valid proof of work, and we'll kind of cover mining a little later in the lecture. And then we pull up a transactions list, and then we say, okay, we're going to go through the state. We're going to, based on the transactions we have, we're going to update the state. And then for the very, very last state, once we reach there, we want to generate some kind of a Merkle route, and we want to check if that's the same as the transaction route that's been provided by the person who's proposed the block. So I want to generate the Merkle proof myself, and I want to check it against the miner's Merkle proof that they generated for me to check. So it's a very easy way to check like tamper resistance. And I return true if that's the case, if they match, and I return false if they don't match. So, and another important thing when it comes to global truth is forks. How many of you have heard of like the term hard fork or soft fork? And most of you probably have. Okay. This is like pretty much what a fork is, except essentially hard forks are people changing client code such that it's no longer compatible after a certain point on the chain, and therefore they completely deviate. Whereas these are more closer to soft forks in the sense that everything is still like compatible with each other. So what happens when we have multiple blocks submitted at the same time in a fork? Does anybody have any ideas? Yeah.
Well, one of them gets orphaned depending on which one's accepted ultimately.
Yeah, exactly. Like one of them has to kind of be like the main one. And eventually, like if I start accepting multiple blocks, they're going to create like splits like these in the network, and somebody is going to have to decide which one of these is going to be like the main chain, right? Yeah, did you have another question?
Yeah, can you explain how the system of miner compensation for uncle nodes works, uncle blocks?
Yeah, we'll get to that.
Okay.
Yeah. So essentially, like because Ethereum has such a fast block time, right, 12 to 15 seconds, it's not hard to have multiple blocks like show up at the same time very, very frequently. So if you have any kind of deviating state, it essentially can destroy your consensus, and a fork is going to occur as a result of these multiple paths. So it forces people to choose which chain they need to go on. So how do we determine which one is the most valid? And the answer to that comes with Ghost Protocol, which is not the Mission Impossible movie. We must be on the blockchain that essentially has the most computation done on it. And one way to determine that is through the block number, which seems kind of like stupid, right? Like you're just incrementing like block numbers as you like submit more and more blocks, but it's true, right? Like as you move more and more towards the latest block number, you see that more computational work has been done for that specific block. But technically that's not always true, right? Because some people could find blocks faster than others, and this is a lottery game when it comes to mining puzzles, as we saw before. So it's like an estimate of like who's done the most work. So if you had two chains and like one chain could technically have done more work than the other because it took longer to find like certain blocks, right? So this is like kind of an estimate that's used for Ghost Protocol. And essentially like whoever like gets the most work on their network, on their chain, which is all on the same network, will be the main chain. So that's why it's called the greedy heaviest observed subtree, which is a very like forced acronym because they wanted to make it Ghost. It's not a really good acronym. And that leads me into talking about world state, which is the underlying thing that we need to come to consensus on. World state is essentially this mapping between account addresses and states, right? And it's divided by blocks, and each block is this epoch in this distributed system where transactions that were broadcasted are then included in this block to alter the world state for a blockchain. And then the state is actually stored within blocks, and it's encoded with recursive length prefix, which we talked about in the previous lecture, and it's stored in a Merkle-Patricia trie, which is a very special data structure. And this Merkle-Patricia trie is then stored in some kind of database, and it has some kind of mapping from like byte arrays to like other byte arrays, and this is how like you store like Merkle-Patricia tries in a database, right? Because usually you have to serialize your data in some way in order to store it in some kind of data structure. So like JSON, for example, is a very, very commonly used format, but a Merkle-Patricia trie has to do something different. And we'll kind of talk about that in lab more. A state database is then essentially it's just level DB for Ethereum nodes. Like if you have Geth, this whole state database that is full of transactions that contains all the Merkle-Patricia tries, all the block data. It stores everything off-chain on some kind of Ethereum, like some kind of Ethereum client on somebody's computer. And this is how people like, access like certain data that's like very old. This is how people run full nodes. It's some kind of database that they access because databases are very fast, right? If you imagine like I wrote this all up in Python and I'm trying to like process like hundreds and hundreds of gigabytes of data, there's no way that's going to scale. There's no way that I'm going to be able to like fetch all that data and make sure that it's like very, very quick to access. And databases have all kinds of optimizations that are used in order to help out with that. And from this world state, we understand that this is what we come to consensus on. Like it's this storage. It's not necessarily computation. Computation is a very separate thing. We come to consensus on the results of whatever computation that's happened, that is proposed by people. So I just want to review RLP encoding, but it's very simple. All you do is, when you take an array and you have some kind of piece of data like a string, you just want to take the byte value for if you have, let's say you have like one element, right? You just want to take the byte value 080, and then you want to take the length of the string, which is 3 in this case, and you just want to add them, and you want to put it at the first index, and then you want to just break up the string into different characters in the array. Can anybody guess like why we might do this in this setting? Why might we RLP encode things? Like who in their right mind would like split this up into like separate characters? Like why would we even think about doing that? Yeah.
To prevent like injection attacks.
What do you mean by that?
Trying to somehow inject like malicious code into your data.
Okay. Well, that's actually prevented through the cryptographic handshakes that clients will do, and like as well as like the digital signatures of like the transactions themselves. So like things are very like hard to tamper with because of cryptography. So the reason why we break this down into like very like separate like pieces of data is because of networking. And in networking, it's not as ideal as things seem to be. You have people like you have people with like buffers on both ends, and you essentially need to make sure like all the data gets into their buffer in some way. And sometimes packets don't get received at the same time. So essentially like what happens in Dev P2P is we build on top of that through this RLP encoding, and we make sure packets get received in a certain order through TCP. But then we also make sure that it's very like nicely serialized for us by splitting up the characters by just like listing it in this like single byte array. So we send a number. We tell the other computer how much stuff we're going to send, and then we start sending stuff over. And then we use TCP in order to like make sure that the ordering was fine. So that's basically like how RLP encoding works and why it even exists, right? The next thing I want to go into is like talking about blocks. So blocks are the stuff you chain together, right? Like I'm sure people have like tried to say this and like it sounds really stupid, but it kind of is true. Like blocks are chained together by means of the parent hash that they have in the current block, and essentially they just point back to the history, and each block essentially makes the network more secure because as you like continually hash and add more and more blocks, you are saying the history of everything is more and more and more correct. So older blocks essentially get more and more confirmations over time. And that's why a confirmation in the network is actually, it actually means that how many blocks have you added on to the end of like another block. That's the number of confirmations a block has. So blocks contain a few things. They contain block headers, they contain a set of transactions, and they contain a set of other block headers for the current block's uncles, and all of which are determined by miners submitting the block, right? So miners will create their own block header, miners will order their set of transactions how they want, and miners will decide like which uncles get included in the block. What the heck are uncles? Uncles are basically, this is a very confusing definition, but there's no really better way to explain it. But an uncle is basically a block whose parent is equal to the current block's parent. And this is because you can only specify omners and uncles after a block is submitted to the main chain. And by the way, omners and uncles, same thing. It's just that omners are just the gender neutral term. And I don't know why they didn't how do you even knew that? Like, this is like news to me. I know that. Did any of you know that before? Okay, yeah, I didn't even know that. But yeah, Ethereum has this thing where they tend to like use weird naming conventions, and it's not great. Like gas, for example, like there's gas. There's gas limit, there's gas used, there's like all these like really terrible names for like what gas is. Oh, start gas, right? Like, yeah, there's like so many different names. So
why does miner need to include the uncle's information? I mean, uncles is not going to be not going to be the part of the chain anyway, right?
yeah, so I'll talk about that. So so with uncles, with this faster like processing on chain with faster block time, you have all kinds of competing block solutions that are popping up all the time because there's so many miners in the network. There's going to be times where people are receiving the same set of transactions, because if you think about it, like transaction ordering, it's not like some dude is like sitting behind a computer and like trying to like drag and drop like transactions in certain places. It's just people running like Geth clients in the background that programmatically like order a set of transactions. So it's very easy for people to come up with the same blocks, right? And if they come up with the same blocks, they basically are competing, right? So with the same blocks, if they don't make it to the blockchain, they become orphan blocks because they end up starting their own fork, and whichever fork wins ends up becoming the main chain, right? And that other person gets screwed over in Bitcoin. But in Ethereum, uncles help reward these people for including these orphan blocks. And how it works is uncles are within the 6th generation of, or less, of the present block. So after 6 children, orphan blocks become stale, and they can't be references anymore. And that makes sense. Like, 6, like if you think about it, like 6 blocks is about, I don't know, like maybe if a block time is like 15 seconds, it's about an hour. It's about a minute and 30 seconds. And I guess that's a lot of time in the Ethereum world. So yeah, six blocks when it comes to uncles. And whenever you use an uncle as a reference, whenever like a miner submits a block, they can insert uncles as references. They can say, okay, I have this list of uncles that refer to some previous block that happened, and I want to include this because I can actually get a reward from this. So whenever a miner chooses to include uncles, they can increase their reward significantly. I believe the amount is 1/32 of the block reward. So the block reward is like 5 ether. So if I submit a valid block, I get 5 ether. If I do 1/32, it's about it's some decimal amount, but ether is a lot. So it's like worth it, right? Because you're making more money, so you might as well include them. And the more uncles that you include, the more that you reference, I believe you can include 2 only, the more money that you can make from this. And anybody who gets a valid uncle block can make a lot of money too. They make about 1/8 of what the block reward is. So think about it. Like if people are submitting like the same blocks, like the person who wins the main chain gets 5 ETH. The next person gets about like 4 ETH, and the person after that will get a little less than that, but it's still a significant amount. So it makes sense for people to want to submit uncles. And what uncles do for the network, the reason why it's designed this way, is because decentralization is kind of important for Ethereum developers. They saw what happened with Bitcoin, and they didn't like how mining pools took over. But then again, Ethereum is also run by mining pools, just not as centralized. But because more people can earn rewards for the same blocks, now we have more incentive to not pool and go out and mine blocks on our own. Now this is still a very hard puzzle to do, so you need pretty beefy setup, or maybe even like a data center in order to like get like blocks very frequently. But yeah, it's not that lucrative, so people still pool. So they realized that was a problem, and now they're just kind of abandoning proof of work and saying, let's move to proof of stake. And uncles also increase security. And the reason why is because every new block that refers to uncles in the past is simply just increasing the security of the old blocks, right? So they're saying like, okay, this person like also solved this puzzle, and therefore it's correct, so we should reference it. I'll get a reward for it. The network will be more secure. More blocks, more data is used to say, okay, things are correct in this network. And that leads me to the block header. And a block header is much more complicated in Ethereum than it was Bitcoin. That's mainly because we have to deal with account state, and we have to deal with gas, and we have to deal with just way more complexity in general. But I'll walk through some of the things. It's kind of like terminology. I encourage you to go and review this on your own. But we have the parent hash, which is the hash of the parent block header. That's prev hash in Bitcoin, so there's like small naming differences. Omner hash, basically the hash of the current blocks list of OMMERS. We have the beneficiary who gets the reward. That includes the transaction fees and the mining reward. We have the state root, which is the hash of the root node of the state trie. Nick, I think, will cover a little more about what the state trie looks like. We also have the transactions root, which is the hash of the root node of the trie that contains all the transactions listed. We have the receipts root, which is very similar, but it's a trie that has all the transaction receipts, and we'll talk about that as well. And there's also a logs bloom, which is a bloom filter, which if any of you have heard of, it's a very probabilistic data structure. It's very quick for lookups. And we also have difficulty, and that changes every block on Ethereum. And we have the number, which is the number of the current block. So we talked about that being used in Ghost. And it has the gas and the gas used. The gas limit in this case is not the same as like the one that you send in a transaction. It is referring to the block gas limit that was specified at the time for whoever like submitted that block. And there's also the gas used, which is the sum of total gas used by the transactions within the block. And there's also the timestamp, which is the Unix timestamp, and it's used a lot for like proof of work and like validating blocks. And there's extra data that's related to this block if you wanna like create some kind of application on top of this, on top of Ethereum. Like you could try to leverage extra data, like some people have done with Bitcoin, in order to create their own protocols on top of Bitcoin. And there's also a nonce, which was used for our proof of work puzzle solving.
What's the purpose of the gas limit? By the time the block is created, we already know how much gas is used. So what is the
Correct. So the gas limit essentially limits, it basically says, okay, this is the max amount of stuff I can fit in this block. In Bitcoin, there's something called a block size. In Ethereum, there is no block size. There's something called a gas limit. I think Nick will cover that as well. So I'm gonna like give a pause here, sign in. The code is bloom filter. You think so? That's good. I think a lot of planning helps. You can pick it up.
Okay. I have half an hour. Hopefully you can get through this next part. It's pretty dense, so hopefully you guys are paying attention. All right. So Ethereum logs. Ethereum logs. Ethereum logs. What could those be? Who has an idea? Events. What do events have to do with logs? Are they the same thing? Excuse my voice, by the way. I'm a little bit sick. So let's find out, right? What are the uses of logs? So first and foremost, a log is the underlying mechanism that an event is tied to. So it parallels what an event is in bytecode, basically. So if you were to look inside, the blocks, events would be represented as logs. That's basically all they are. Now, why are they useful? It's on the board.
They're a lot cheaper than other forms of storage.
So they can be used as storage. Now that is novel, right? Why is that novel? Why are they cheaper? So they are not stored on contracts, right? They can't be listened for on contracts. The only way you can interact with them as a developer is through JavaScript, right? Or any other framework. And so what you can basically use logs for is to keep track of certain events over a period of time. Keep track of certain occurrences that have happened to a wallet over time. Without having to store the state of the contract or query the contract. Another use for this is that actually when you call send transaction, a lot of you came to me with this problem yesterday of, oh, I'm just getting a return of like some garbage, like some transaction data. Why am I not returning like, 1 + 1 is 2? Why don't I get that 2 back? Why am I getting this transaction back? Are you guys familiar with the issue I'm talking about? Hands up. Okay, not many people develop with Solidity, it seems. You can also listen for the logs. So your front end can actually be there listening to certain events that happen and then trigger subsequent occurrences on your browser window or on your dApp, if that makes sense. So logs stored in the block header come from log information contained in the transaction receipt. Now the transaction receipt I want to highlight is different than the transaction itself. You can think of, I think actually there's a slide on that later on, but basically what logs contain is an address of the logger, topics that represent various events carried out by the transaction, and then any data associated with the events. So basic stuff you want to log in any case. So what the event was, any associated data, and who was responsible for the event, right? And these are what logs look like, and those 3 fields that we highlighted can be seen in 2 examples. Here is just the raw CLI version, and over there you can see maybe like an Etherscan, some GUI version. So if you ever see data like this, now you know what it means.
Who decides the topic? I mean, how the naming convention of topic?
So the topics are set. The first one, I believe, is more special than the rest of the 2. So it's usually kept at a maximum of 4 topics, and we can highlight more details on Piazza if you guys are interested. But topics basically highlight the type of event that was fired. Okay, and so in this example, we have the event person created, right, which takes in 2 uints. And if you'll recall from the docs, uint defaults to uint 256, right? So that's important, right? What ends up happening is that when you fire in foobar, in the function foobar, when you fire person created, what it's going to do is it's going to create a hash of person created with 2 arguments that are uint 256s. Everything makes sense so far. We're on the first bullet point.
So it's just
Yeah, and then the values are actually done separately. So they're going to do age and then height separately, if that makes sense. Now, what is Kekuk 256? Maybe a minor note, maybe important, may not be. So it's a hash function. It's the precursor to the standardized SHA-3 function. So if you were to look it up, sometimes it's referred to as SHA-3 256. Yeah, so keep that in mind. It might pop up sometime down the line. The reason they did that, the reason they used that hash function instead of the regular SHA-3 is just a timing coincidence. The SHA-3 function wasn't formalized at the point where they were ready to deploy the Ethereum network. And so this is actually, some people were also asking me about a listener, what a listener would look like. And so I included one just for you folks. Okay, so getting into transaction receipts, as I mentioned, transactions are not transaction receipts. Transactions are the request vectors. You can think of them as, if you recall what we talked about with the RPC calls that interact with ABIs, and then transaction receipts are the outcomes, the recordings of the outcomes that occur as a result of the transaction. So this is the difference between the two, and it immediately becomes clear, what is useful in each of these. I'd like to point to, in the transaction receipt, the post-transaction state and the cumulative gas used. Those are two things that, as you can imagine, might be important, especially cumulative gas, specifically for measuring things like block gas limit. Does everything make sense so far? Have I lost anybody?
You haven't lost me, but I just have a question.
Go ahead.
Like, what exactly is the post-transaction state?
Yeah, so I launch a transaction. I call a method on a contract.
Yeah.
The post-transaction state is the state of the virtual machine, the address space, the contract, what the contract holds, after I launch that transaction, if that makes sense. Okay, and actually, everything on the transaction receipt list should become clear by the end of this. Okay, so I just mentioned everything would become clear. The very last item we have is a Bloom filter, right? What is a Bloom filter? So it's somewhat of a sophisticated data structure. Akash talked a little bit about it being a probabilistic data structure. And what do we mean by that? So this example is pulled directly from Wikipedia, but I think it's a good one. And so you have a data set, XYZ, up top. And so with XYZ, you define a k of 3, and k is just some arbitrary number you choose. And k equals 3 means you're using 3 different hash functions. And so you're going to map each of x, y, and z using those hash functions, those 3 hash functions. So you're going to map 9 different values, right? Okay. So you're going to map 9 different values, and you're choosing your m to be 18, which is basically the space of the values. So you initialize your space to be all zeros. And when you map x, y, and z to the space, you register them as ones. Very simple. So henceforth, if I ever want to check whether x is included in the data set, all I have to do is hash it 3 times with these 3 different hash functions and see if there are ones in the spaces of this Bloom filter that I have. Have I lost anybody there?
Could you explain that again?
Yeah. It's not an easy concept, so I know you guys have questions. So the Bloom filter itself, you can think of the Bloom filter as the series of ones and zeros. And so if I take x, just think about x, and I hash it in 3 different ways, I'll have 3 different ones out of the 18 zeros, right?
Yeah.
3 of those will be ones. Now, if I give that Bloom filter to you, and you want to check whether x is in the Bloom filter, all you have to do is hash it again, check if there are ones in those positions, which there will be. And I do the same for y and the same for z. Now, what that means is that you will never have false negatives, right? If but you could have false positives, because the hashes make so these are not collision resistant in this case because the space is limited. So certain inputs may have the same outputs, and certain overlapping inputs may result in different outputs. So say
Making your m bigger help.
it would help, yeah. And choosing your hash functions more specifically would help. But again, you can never avoid false positives.
The false negatives won't happen.
You can never have false negatives. Yeah, that's one of the properties of this.
Yes, hash function. That's always good. Yeah.
And so the cool thing about this is that it's very applicable to various things. I mean, Medium uses it to avoid recommending things you've already read. But in the case of Bitcoin, now we're deviating from Ethereum a little bit. This is the way Bitcoin does things. And so if you'll recall what an SPV is, anybody? It's a light client, simplified payment verification. And you have a full node, which is basically a miner. And SPV will generate a Bloom filter of the transactions it's interested in, right? And so the full node will basically look through every single transaction that has ever occurred on the blockchain, and it'll compare against this Bloom filter. So what ends up happening is that the SPV never ends up having to deal with a ton of transactions. That's the full node's job. The SPV only gets the correct transactions, right? Oh, wait a minute. Didn't we talk about false negatives? Or false positives, I mean? Don't let that confuse you. So yeah, false positives happen. But that's not an issue because they happen not often enough that it would be a problem. And also, the SPV can just discard it because it knows what it's looking for by default. Is that clear? Okay. So then what happens with Ethereum? Well, in Ethereum, SPVs can actually listen for specific transactions that they're looking for. So direct your attention to what's on the right for now. And so first of all, they'll look at a new block, and the new block will have in its header this collated, this union of every other Bloom filter in the block. So every transaction receipt has its own Bloom filter, but the union of those is then collated and put in the block header. So the SPV can look at the block header and see if there are any transactions in that block that interest them. And then if there are, they look inside the block. But if there aren't, they don't have to bother. They can just move on. And they can just keep listening for the next block and the next block and the next block. And you can see how this saves them a lot of time. Now, what's a situation you would want something like this? Think about syncing your wallet. You only want transactions that are relevant to your wallet, right? You have an exchange. The exchange doesn't want to be running full nodes for every single person, monitoring the wallet transaction data, but they want to be listening for their users' wallets, right? And so for every new block, they're going to look and see if there are any transactions pertaining to their user's wallet. And if there are, they'll look inside the block and record their updates for the user to see. And that's how you see your updated balance. And if there aren't, then good. We'll just wait till the next block. All right. Everything okay so far? Cool. All right. So block size. What is a block size in Bitcoin?
1 megabyte.
I think it's a little bit more than that right now, but so it's defined by basically the space it takes up in storage, right? It's defined in bytes. But Ethereum doesn't have block size. Akash started talking about it. What does Ethereum have? Block gas limit, right? And so the way it limits the amount of transactions that can be included within a block is through this gas limit. And so this is a visual example for the visual learners out there. And so say we have a block on our chain, and its gas limit is 10 gas, right? And we have our mempool. Okay, what is our mempool? What is the mempool? Unprocessed transactions. Okay, awesome. Oh, okay. So say we set our block gas limit to 100, and we have these transactions in our mempool right now. They're obviously very simplified version of transactions. So we have transactions 0 through 5, and each of them have a different amount of gas that was taken to run them, right? Okay. And so what is a good combination to include in our block right now? I'll give you guys a second to think about it. We can go up to 100. So potentially, what we could do is we could choose 2 and 4, right? And that gives us 98. So that's pretty close to the limit. We could also go with 0, 3, and 5. That's also 98. That's pretty efficient. Okay, but what is the is it better to include more transactions? Which one would you pick? Who thinks they would pick the one with more transactions? Who thinks they would pick the one with less transactions? Nobody. Okay. So basically, if you guys in the front row, who are the only ones who voted, picked the more transactions, and I picked the block with the least transactions, I would most of the time get that block. So if we were mining, if we were competing, I would get that block most of the time, if that makes sense. Because the more the block grows in terms of transactions, the higher the latency in propagating that block. Does that make sense?
So gas limit is determined by the miner before you start mining the block.
So it's interesting. The block gas limit is kind of set, and it's also kind of not, because it can be changed by the miner's client. And it's like a voting system, but it's not a voting system. And I'll explain that in a second. But before I get to that, I want to introduce like this problem the fact that you can propagate a block way more quickly the more empty it is means that people are somewhat encouraged to include empty blocks.
Would the gas price also influence which transactions you choose to include?
So would the gas price influence which transactions you chose to include? Yes, indeed. Yes, indeed it would. So obviously you would want the transactions that paid you more per transaction. The examples here are more in terms of efficiency, in terms of filling the block. Yes?
So kind of follow up to that question is you mentioned like, so for example, the gas prices for both of these like groups are the same at 98. Why does like matter the number of transactions?
Yeah, so the more data you include in a block, the heavier the block gets, right? The more megabytes you'll have to transmit over a network, or the more bytes, I guess. Now I want to draw a distinction between people are using gas price a lot, and that can refer to two things. that can refer to the amount of gas it costs to run transactions, or it can refer to the price of gas in ether. And so in the real world, people would be incentivized more by the amount of money they receive, by the amount of ether they receive, rather than the amount of gas included. But keep in mind, despite that, we're still limited by the block gas limit, which does vary based on the gas itself, not the ether. I hope that was clear. Now, back to the question of how do people decide the block gas limit. So essentially, people can vote, and the current miner who proposes the next block is able to change it plus or minus 0.1%. And so you can see how it's a voter-like system in that across the chain, people are going to trend towards what they think is the proper gas limit. So plus 0.1, plus 0.1, plus 0.1, oh, minus 1.1, plus 0.1, etc., etc.
So at any given point in time, there is, for the last block on the main chain, there is a given gas limit.
Yes, and if you are the person proposing the next block, you can choose to change the gas limit by that amount.
Do you know what is it roughly right now?
Oh, I have no idea. Go to what is it? Ether gas station, and it'll tell you. Yeah. Okay, so hash structures. Flying through this real quick. Merkle trees. Does anybody know what a Merkle tree is? Has anybody seen Merkle trees before?
Yeah, it's on the application.
Yeah, it was.
So I can answer this, but first I want to ask, like, what was the answer to that you know, like, why can't we DDoS the network by just sending out a bunch of empty blocks? You know?
Yeah. So the thing is, you still need to do the same amount of work as before, as with including transactions. So you can't DDoS the network. The issue is that it doesn't actually move the state forward, right? It doesn't actually help any of the users of the network process their transactions. But also it makes less money, right? So, you know, trade-offs. And that you can actually see a few, maybe I can post a graph on Piazza that I found where there was a period of time where people were just sending empty blocks, valid empty blocks, for some strange reason. Yeah, weird trends. Nobody knows why. Okay, Merkle trees. So, okay, maybe let me talk about what a Merkle tree is, what it does, and then what it's used for. So, you have transactions A, B, C, D, E, F, G, H, and you want to store them in an efficient manner. So one thing you could do is you could hash them all together. Simple. Another thing you can do is you could do this, right? You could hash A and B together. You can hash C and D together, E and F together, G and H together. And then you can take the hashes of all those, so the hash of A and B, and hash that with the hash of C and D. And same with E, F, G, H. And then you take the result of both of those and hash them together. And that's your header, right? And so this is okay. Actually, why don't you just do this? Why don't you just hash them all together like this? Why do you need to go through that complicated process?
Because once you get the verification of a particular transaction.
Right, Morgan?
Ordering, I guess.
Ordering matters in both cases.
Okay.
Yeah, because if you swap C and B, the hashes will be completely different.
All right. So I guess if you just hash them all together, does the order matter?
Yes,
Okay.
it also matters.
It takes longer to find out which transaction you change.
Yeah. So exactly, both of you are right. So for in the process of like validation, it's way easier by a factor of log, I think, to use these structures to validate as opposed to this. I think this is just constant time. Whereas with this, if you want to validate that C it was indeed part of the set of transactions, all you have to do is hash it with D you already have the other hash and the hash over here. So you basically avoid hashing 4 different transactions. And this is kind of a trivial case. You can't really see the benefits. But imagine, a hash structure with 2 to the 10 transactions, right? It gets pretty crazy. This is just a 2 to the 3 amount of transactions, right? 8? Yeah.
So it's like a binary tree that you just start looking your transaction at this side and then keep dividing and
Yeah. So for any tree, if you want to include a transaction, if you want to see if there's a transaction that's been included somewhere, like the whole other parent branch will have been already computed. So you don't need to recompute that side, if that makes sense. And then for every sub-branch, the other the mirrored sub-branch is also computed. You can see that over here, right? So like in this sub-branch, this side is computed, and in the grand scheme of things, this whole branch is computed. Anyway. Okay. And so we have Merkle-Patricia trees, which are actually way more complicated structures. We'll cover those in lab. A few Merkle. So Ethereum doesn't actually use Merkle trees. It uses Merkle-Patricia trees because they're way more useful. And 3 main things you want to keep in mind are the receipts and transaction routes, which are the ways in which blocks store those receipts, those transaction receipts, and the transactions. So you'll find those inside the block, and you'll also find the state root. The state root is what keeps track of things like the address space and contract state. So things like code, things like the values they're stored, their storage, right? And their address, of course. Anybody confused so far? Great. So mining, this is the last topic. Let's see, 10 more minutes. All right. All right. So block difficulty. Who knows about block difficulty?
It's like represented by some target value with leading zeros.
Okay. Okay.
It can fluctuate. That value can grow larger or smaller.
Okay.
Which means
That.
the difficulty goes up and down.
Okay. Yeah. So that's the case in Bitcoin, I think.
Okay.
Yeah. But yeah, you're right. It does fluctuate. And it goes up and down, and it varies with the speed at which Sorry.
the speed with the blocks are being generated.
Right. So if the previous block was mined faster, then the network difficulty goes up, and et cetera, et cetera. And so what is this? Or rather, do you guys remember how this was represented in one of the first lectures? So in one of the first lectures, we had a target that we were trying to hit, and we.
And you keep like scaling it up and down.
Yeah, and we were kind of changing the target zone, right? And so this is the more formal way of thinking about that. Yeah, nothing much else to say about this. Hang on a second. Okay. Yeah. So a few things about mining. Each OMMER within the block header must be a valid header, right? And be within the 6th generation, which is what Akash talked about. Otherwise, it's what? Stale, right? Okay. So, and the gas used number on the block must be equal to the cumulative gas used by the transaction listed on the block. What does that mean? So I think there's a mistake in the header over here. But regardless of that, what does that mean? So you go through each of the transactions in a block, and you look at the gas used value on the block, and if they don't match up, that's a problem, right? You know something's up. Okay, a few more things. The miner who successfully proposes a block, they're rewarded 5 ETH. I think it's changing to 3 at the moment. Yeah. Or maybe it has already changed. I'm not quite sure. Yeah. So for each OMMER, the current block's beneficiary is awarded an additional 1/32 of the current block reward. And then also the beneficiary of the OMMER blocks gets rewarded as well. So not only does the person who mined the block get rewarded, but the person who mined the OMMER that was referred to in the block also gets rewarded.
How is the block reward determined?
How is the block reward determined? I think it's set, but miners decide to decrease it or increase it based on EIPs.
So it's ad hoc. It's not like Bitcoin where it's predetermined after so many blocks it goes down to 12.5 and all that.
Yeah, so the thing with Bitcoin is that it's a deflationary currency, so it's finite. Whereas with Ether, it'll never run out.
But what's the incentive to reduce it versus if miners are voting, they should always vote to increase it?
Yeah, I assume there's a lot of reasoning that goes behind it that I'm not aware of.
So OMMER actually, the owner of the OMMER blocks, they never get rewarded for anything.
The owner of the OMMER blocks?
Yeah.
No, that's not true, right?
That's what they get.
Because if they get referred to in a future block that is mined, that is successfully mined on the Logness chain, then they get rewarded, yes.
Oh, okay.
Yeah.
1.8.
Yeah.
You said 1.8.
Yeah, I think that's what Akash said. And so in the final step in verification before the mining, like before the proof of work starts, right, is verifying that the changes have been applied correctly, right? Yeah. So that checking that the new state matches with the state root, for example. So you hash the new state, right, in the same way that every Merkle-Patricia trie is hashed, and you check it against what's included in the block that you got. Does that make sense? Is anybody confused about that? That's actually a difficult point to grasp.
Can you repeat that?
Yeah, I can. So you get the block, right? And the block tells you to run a bunch of transactions that make changes to your local state, to your local blockchain. They also send you a Merkle-Patricia trie, or the hash of it, the header of it, right? You go back up here. They send you the header, right? And so you're going to take your state, your new state, and you're going to hash it in the same way, and you're going to compare tries, and you're going to compare headers. And if they match perfect, you've both arrived at the same new state, and which is what should happen because it's deterministic, right? But if it doesn't happen, if the packet was corrupted along the way, or somebody's trying to spoof you, then obviously there's a problem. You reject the block. Okay. I don't think we need to linger on the block rewards, but ETH hash. So this is the proof of work mining algorithm. The result you want to arrive at is the mixed hash and the nonce, and the inputs to that is this proof of work function that we'll actually cover in a second. We have, again, 2 minutes. And so you put in the new block's header, without the nonce and mixed hash, the proposed nonce, so you're guessing the nonce, and also a DAG. And so mixed hash is a hash that, when combined with a nonce, proves that the block carried out enough computation, and a nonce is a random string of, it could be anything, but in this case, ones and zeros, and when combined with the mixed hash, it proves that you've done the computation. And this actually is a lot of detail that you would not need, or you could go over on your own. But the most important thing here is to see how ETH hash actually works. Again, ETH hash is the algorithm. It used to be called Dagger Hashimoto because it was a kind of a convolution of two different algorithms used for memory hardness. Now, why is it important for this algorithm to be memory hard? What does it mean to be memory hard?
You don't need a very high-end computation power to be able to mine.
Okay, that's the consequence of being memory hard. So memory hard means that it's very memory intensive, basically. It's a memory intensive process. And so the computer that you're using needs to have good memory, in simple terms. And coincidentally, computers like ASICs, which you'll recall Bitcoin has this centralization issue where ASIC miners have basically taken over. If you don't have an ASIC, you can't mine, right, on the Bitcoin network. And for the most part, ETH hash is ASIC resistant because of the memory hardness properties of this algorithm. And so the important thing here to note is you have the pre-processed header and the current nonce. So you guess a nonce, right? So we're starting at the green. And you input it into, it says SHA-3-like function. We already talked about the SHA-3-like function. In this case, it's Kekek 256, right? And you come up with a mix, right? The mix is 128 bytes, right? And you use that mix to fetch some information from a DAG. Now, the way the DAG works is that over a certain period, you have a seed that generates a cache, and from the cache, you select a random subset to generate this DAG. Now, again, that's not too important. It's all in the details that we skipped. But the important thing here is that you use the mix to fetch from the DAG, right? So generating the mix is not memory intensive at all. But actually fetching from the DAG, you can see the bottleneck over here represented. That's what is so memory intensive. Pulling the DAG information, the DAG data, into your cache. And again, this has to do with L1, L2 caches, which are meant to be fast. And then, of course, after that, you take hits in performance. Has anyone taken 61C? One, taking it. Okay. Anyway, so you pull data from the DAG, and you use that in your mixing function to come out with the next mix. And you do that 64 times. So that's what's happening. So we've gone through step 1, 2, 3, 4, 64 times, right? And we get to mix 63. And this is all still 128 bytes, right? And so there's a post-processing function that condenses that into 32 bytes. And that 32 bytes is then compared with the target threshold. And if it's less than or equal to the target threshold, if you've hit that target that we were talking about, you're A-OK. You're good. You've mined the block. If you haven't, though, what do you have to do? So you reject the block, but then what happens? Do you give up?
You increment the nonce, current nonce.
Yeah. You pick a different nonce, right? And you start again. Again, mixing it 64 times, pulling out data from the DAG.
How are you picking the nonce?
Randomly.
Totally random.
Yeah. Okay. Yes.
How's the DAG get generated?
Yeah. So okay, we can. We're actually past time, but we can go through that. So, all right. So seed is calculated right at the very beginning, and it's different for every epoch. And so it starts off as 32 bytes of zeros. And the next one is decided on the hash of the previous one, if that makes sense. So using this seed, you generate a pseudo-random cache. Right? Why pseudo-random? What is a cache? Okay, pseudo-random because in a deterministic system, you can't really introduce randomness, so it has to be artificial. And then what is a cache? You can just think of it as a repository of data for now. Okay. After that, you use the cache, you generate a DAG data set, and again, it's deterministic. So the important thing here is that to know that given a certain seed, you can always arrive at the same DAG. Right? You can generate the same cache, generate the same DAG. One thing we haven't talked about is that with the DAG, it grows over time. So when it first started, it was around 1 GB. Last year, it was around 2 GB. Don't know what it is this year. And then finally, we get into the mixed hashes that we saw over here. And then a little bit on rationale. These are the properties that the Ethereum team had in mind when they were building ETHAsh. And I think they're all pretty intuitive. I/O saturation is exactly the bottleneck we were talking about when fetching from the DAG. GPU friendliness, because CPU mining isn't advised, isn't desirable. So people want the ETHAsh to be able to be carried out by GPUs. And then every other property is to allow light clients to be able to catch up with the network really easily, to allow them to be able to verify easily, etc. And all those are explained later on. Now this one is very interesting actually, because despite wanting to make things easy for a light client, they're also putting artificial barriers there. They're saying you should not, with a light client, be able to do mining, to act as a full node, if that makes sense. If you want to act as a full node, you should stake some resources. You should buy a proper machine. You should spend money on electricity. You should do work. So that's the rationale. Anyway, thanks for your time, guys. I think that's all we have. Yeah.